Let's look at example number 1. In this video, we're going to continue with applying the fundamental theorem of algebra to find solutions to polynomial equations. Now, we've learned a few different ways that we can identify the solutions. We learned how to factor, and there's different types of factoring. One is factoring by grouping. So when I look at this, I see a pattern. And so will this always work? No, but sometimes it will. And so instead of me going ahead and listing the factors of 18, 1, 2, 3, 6, 9, and 18, and then listing the factors of the leading coefficient, which is plus or minus 1, and then I go ahead and attempting 1 and negative 1 and 2 and negative 2 and so on with synthetic division, I see a pattern here. I can factor out an x squared, and I'm left with x squared times x is x cubed. X squared times 2 is 2x squared. Is there a value that I can take times x and achieve a negative 9x? Negative 9 times x is negative 9x, and negative 9 times positive 2 is negative 18. So in the front and back, we both contain an x plus 2. In front of the first, parentheses x squared. In front of the second is a negative 9. Remember that when we're finding the solutions, that's both the real means where we can see them on the x-axis, where the actual function crosses the x-axis is the real solutions, and the complex contains the i's, the solutions that contain i's, and those are not visible on a general xy axis, which is only contains reals. Okay, so I have both of these. I'm going to set both equal to 0, and I'm going to solve. I'm looking for 3 solutions. X plus 2 equals 0, and x squared minus 9 equals 0. So one solution is negative 2, and this is real. 2 solutions on the opposite side, plus or minus the square root of 9, which is 3. And so I have solutions of negative 2, positive 3, and x equals negative 3. So I have 3 real solutions. That means for this particular graph, I'm going to have a solution at negative 2, at negative 3, and at positive 3. Notice that we have an odd degree and a leading coefficient that is positive. So up on the right, down on the left, negative 18 is going to be the y-intercept, and it's looking something like this. All right, so in example number 2, we're looking at another polynomial, and we're trying to identify the 3 solutions to this polynomial. So I'm going to replace y with 0. As a reminder, if I can't do factoring, in this case factoring by grouping as a way to find the solutions, then I would go ahead and list all of the factors of the constant and the factors of the leading coefficient. And so even if you're not comfortable with factoring by grouping, that would be a way in which you could use synthetic division to identify the solutions. All right, let's move forward here. So I'm going to go ahead and go, just like example number 1, I can factor out an x squared, and I'm left with x minus 3 in parentheses. And then I'm going to say, if this is possible to solve using the factoring by grouping method, there will be a value that I can take times x and achieve positive 4x. So that would be positive 4x, and positive 4 times negative 3 is a negative 12. Both the front and back contain x minus 3. In front of the first parenthesis is x squared, in front of the back parenthesis is positive 4. And just like example number 1, I'm going to set each of these factors equal to 0, and I'm going to solve. Make sure to show your work. That is required on the AP exam. So without full work shown, they're not going to give you any credit. Even simple steps like this that I know you can do in your head. One real solution is x equals 3. And going back to last week, here's where we applied this new concept of imaginary numbers or complex solutions. I'm going to have 2 answers, but I can't take the square root of a negative. So that negative comes up front and becomes an I. And the square root of 4 is 2, so x equals plus or minus 2i. So I have 3 solutions. 1 is real, and 2 are complex. I'm going to come back to example number 1 and remind you, this is standard form. For me to take these three solutions and write as the product of linear factors, it would look like this. Y equals x subtract, and x subtract. Now in these positions, I'm going to take it and replace those with what I identified the solutions to this problem to be. So I'm going to drop in -2, 3, and -3. Now two negatives make a positive, so that's x plus 2. X minus 3, two negatives make a positive. The order you write these linear factors does not matter. I'd like you to press pause if you're watching this, not in real time, and I'd like you to take these three solutions, one real and two complex, and now write it, this polynomial equation, as a product of linear factors. Come back to the video when you're done. Let's look at example number 3. Example number 3 is going to leave me with 3 solutions. And so I'm going to move forward and I'm going to come up with all the factors of 54. Now if you need to use a calculator, grab a calculator. So off the side here I have plus or minus 1. And if you're wondering how do I come up with these, you're going to divide. So 2 divides nicely into 54. So I know I'm going to have 2 and I'll also have 27. I must have right a little bit smaller here. So 3 goes in, so I'll have 3, and I'll also have 18. So 4 provides 15.5, so I'm not going to write down 4. We know 5 doesn't go in, but we can see that with the decimal. 6 does go in 9 times, so 6 and 9. So these are the numbers that I'm going to test. Let me start. What makes it nice about example number 3 is the leading coefficient is 1. So I'm going to start by testing 1 and -1, and then 2 and -2, and so on. My goal is to get down so I only have a trinomial remaining. Let's try 1. And we can keep this calculator close by in case we need it for multiplying or subtracting. 1 times 1 is 1, add down to get 6. 1 times 6 is 6, add down to get 25. 1 times 25 is 25, add down to get -14. Multiply, and so I already know it doesn't work because I know these two are not going to combine to give me 0. So I don't honestly need to take time to even combine those to get a -68. I know if this isn't 0, 1 does not work. Let's try -1. Once I drop down the first number, I'm going to multiply and add, multiply and add, multiply and add down, multiply. Oh, I get 1 that works. So I know that -1 is one of the 4 solutions. X equals -1. So this has no x's, 1x, 2x's, and 3x's. And I'm going to now continue, to try the values. So I could try -1 again because there could be a duplicate. We're going to see how 2 works here in just a second. So 1, 4, 15, and -54. So I've tried 1. If 1 doesn't work in the initial polynomial equation, it's not going to work again. But if -1, for instance, does work, it could work again. So I'm going to try 2 and -2 and 3 and -3. But if none of these work, I can go back and try -1 again because once again, we could have a duplicate answer. It could be x equals -1 and x equals -1. If that's not making sense, remember duplicate answers are going to bounce off. When it occurs twice, it's going to bounce off the x-axis when we actually graph it. All right, let's try 2. So I'm going to drop down the first number and multiply. Add together and multiply. Add together and multiply, and there we go. We can see how 2 works. 2 does work. So why do I like this? I like this because now when I write this, 0 equals 27, no x's, 1x and 2x. So when I take a look at this, my first goal will be to solve this in the easiest way possible. By solving, I'm trying to find the 4 solutions. I already know 2 of them, -1 and 2. So let's see, is this factorable? 1 times 27 is 27. What multiplies to equal 27 and combines to equal 6? 1 and 27? No. 3 and 9? Well, 3 and 9 would only work if they were different signs. So -3 and +9, the difference is a +6, but then the product is not a +27. So what does this tell me? It doesn't tell me I can't solve. It just says I can't solve using the factoring method. When that's the case, we're going to use the quadratic formula. So I'm going to put parentheses, and then I'm going to drop in the values for A, B, and C. B will be the value, that's with the x, it's a +6, so 6 goes in these 2 positions. A will be what's in front of the x squared, and C is at the very end here. X equals -6 plus or minus, all right, 36, 4 times 27, well that'd be I think 108, but let's check. 4 times 27 is 108, so minus 108 all over 2. 36 subtract 108 is -72. Now I'm going to provide myself a little more space, so I'm going to come back up here and write down my last step. I know that we cannot take the square root of a negative value, so that's going to come out front and become an I. And now I know that the square root of 72 does break down, and I'm looking for the largest perfect square that nicely divides into it. So I'm going to write down the perfect square here. 1 times 1, 2 times 2, 3 times 3, 4 times 4, whoop, forgot, 5 times 5, 6 times 6, 7, 8, and so on. Okay, 64 does not divide in. 49 does not divide. Oh, 36 does. 36 times 2 is in fact 72. We can see that. 36 times 2 is 72. That's going to be 6 times the square root of 2. And now this 2 is going to be shared with like terms, which is the integer values to the left and right. So -6 over 2 plus or minus 6 over 2. And then the proper way we write this, we call this a complex number. Complex because it consists of a real portion and an imaginary portion. -3 plus or minus, and we're going to write the actual integer in front. So 3i squared roots of 2. These are my two other solutions. So this polynomial equation has 2 real solutions and it has 2 complex. We're asked to write our solutions as a product of linear factors. So I'm going to start by writing y equals, and to get started I'm just going to set everything up like this. And then I'm going to drop in both the real and the imaginary portions. So I'm going to drop in a -2 and a -1 and a +2. And this is going to take a little more time here. So 3 plus 3i squared roots of 2 and -3 minus 3i squared roots of 2. Okay, 2 negatives make a positive. So x plus 1, then x minus 2, and then I have to distribute this to both terms inside. So x plus 3 and a negative times a positive minus 3i squared roots of 2. X, 2 negatives make a positive, plus 3, and a negative times a negative is a positive. Let's look at our final answer. So in our final example, I can see no pattern here, I don't believe. I'm looking, that doesn't look like that's going to work. And what I'm looking for, if you're wondering, as I was looking to see, could I solve by using the factor by grouping method? So what I'm checking here is this gives me 2x cubed and subtract 3x. Okay, that works. And this would be plus 4, so that would be 8x. Okay, that is working. And this is -12. Hey, that looks like it works. When I set y equal to 0, this may be a way that I can find the solutions. They both contain a 2x minus 3. In front of the first is x squared, and in front of the back is a +4. I'm going to set each one of these equal to 0, and then I'm going to solve. Remember, even all these tedious steps, you do need to show your work. So I have one real solution because it doesn't contain an I of 3/2 or 1.5. Two answers, can't take square root of a negative, and the square root of 4 is 2. So I have an answer of 3/2, of 2i, and of negative 2i. Two complex solutions. Complex solutions always come in pairs, and one real. Now, how do I write this as a product of linear factors? Y equals x subtract 3/2. We're going to come back to that in a second. X minus 2i, x minus negative 2i. Okay, in this position, 3/2 cannot be reduced. We're going to take that bottom number, not the smaller number, the larger number, the denominator, and we're going to push it up. So 2x minus 3 and x minus 2i, two negatives make a positive, x plus 2i. All right, so now we're going to take what we learned how to do in a previous lesson, we're going to apply it when we have complex solutions. So this next example, example number 5, we are told we have solutions of 3i and negative I. And we want to create or write a polynomial function with these given zeros or solutions. So let's get started. Let's write this right now as a product of linear factors. So x subtract, and x subtract. And then in those positions, I'm going to drop in the solutions of 3i and negative I. X subtract 3, x subtract I, and x, two negatives, this was a negative, makes a positive. Now it is always going to be my suggestion to take these two that are called conjugates, or the same thing but one's positive, one's negative. It's always going to be my suggestion to multiply those first. That will make life much easier. So I'm going to use the box method, which we learned in a previous lesson. I'll write this one on top. There's an x and a negative I and an x and a positive I, and I'm going to multiply. X times x is x squared. X times negative I is negative xi. X times positive I is positive xi. A negative times a positive is a negative, and I times I is I squared. Now I know that I squared is the same as negative 1, so I really have negative times negative 1. A negative times negative 1 is a positive 1. These two are exactly opposite of one another. They're additive inverses. They cancel each other out. So when I multiply these two linear factors, I end up with x squared plus 1. When I multiply these, I end up with x squared and plus 1. Then I would still need to take this factor times this factor. So I'm going to go with the box method again. X minus 3 and x squared plus 1. Some students say it doesn't matter if the x plus x subtract 3 goes on top or if it goes vertically on the side. It doesn't matter. Multiplying, oh, I see a mistake here. I do want to change up one thing here. To make my life easier, I'm going to rewrite this, and this would work, but I'm going to, well, you have two options. One option is to recognize x minus 3. One option is to recognize that we have an x squared and a plus 1, but there's no x to the first power, so we can write 0x to the first. So you can achieve the right answer like this or like this, and however you want to set it up. Multiplying, I get x to the third, subtract 3x squared, plus 1x, and minus 3. And you're thinking, why would I take time to do this? The only reason why is here when I write this out, I need to look, okay, there's only one box that has an x cubed, one that has an x squared, one that has x to the first. So this is what I'm able to achieve. Now over here, I just want to demonstrate how we can get the same thing. X cubed, subtract 3x squared, 0 times this would just be 0x squared, be 0x plus 1x and minus 3. And so here we have our x cubed combines to give you a negative 3x squared, combines to give you a positive 1, and combines to give you a negative 3. Your choice on which one you'd like to do. Let's do one more. In our last example, we're going to go through the same thing. I have 3 different solutions, so I know my final answer will be x to the 4th. 4 solutions, 2 are real, 2 are complex. I'm always going to take care of the complex first. They come in pairs. So I'm going to start right now with y equals x subtract. I'm going to leave a little more space here, x subtract and x subtract. In those spaces, I have 2 minus 3i, 2 plus 3i, 0, and 3. X minus 3. Now x minus 0 is the same as simply putting x down. When I distribute the negative, I get x minus 2 minus 3i. And when I distribute, I get x minus 2 plus 3i. I'm always going to suggest taking care of this first. So I have 3 and 3. So let's make a 3 by 3. Multiplying to get x squared, negative 2x, negative 3ix, negative 2x, positive 4, positive 6i. Then we have a positive 3xi. The order you put the x and the I in doesn't matter as we're doing this quickly. Minus 6i, and negative 3 times positive 3 is negative 9i squared. Now I know I squared is the same as negative 1. I end up with a positive 9. All right, let's look through this. I have x squared, and then I have subtract 4x. Notice that these are additive inverses right here, so they cancel out, as well as these are additive inverses. 4 plus 9 is 13. That's what I'm able to achieve when I multiply these two factors. Now, when I take x times this, I have x squared minus 3x. And now it's my job, and you can either use distribution or you can set up the boxes. So one needs to be 3 across because I have 3 terms. X squared minus 4x plus 13, and the other needs to be 2. X squared minus 3x. Okay, here we go. X to the 4th minus 4x to the 3rd plus 13x squared minus 3x to the 3rd plus 12x squared minus, 13 times 3 is minus 39x. When I combine like terms, there's only one that has an x to the 4th. Now to the 3rd would be, a negative 7x to the 3rd, a positive 25x squared, minus 39x, and there's no number in the back, so you're welcome to put a plus 0. That's really up to you. What I want to see us do is I want to see us go ahead and graph this and see if we can identify. Remember, on a Cartesian plane, when I bring this up, we can only see. Okay, so I've gone ahead and I've graphed this, and we can see this graph now visible here, and we can see I have roots at 0 and at 3. And that's exactly what I identified. I identified the roots at 0 and at 3. At 0 and at 3, again, these are not going to be visible in a Cartesian plane.